Hi, this is a presentation on Clinco-Genomic data analysis using Metabase and GenomOncology. My name is Ian Maurer. I'm the Chief Technology Officer for GenomOncology. GenomOncology was founded in 2012 in Cleveland, Ohio. We have over 40 clients, including 17 NCI and NCCN designated cancer institutes. Our software can be installed on the cloud or on-premise behind your firewall. Our solutions are HIPAA compliant and we take no data rights. This is going to be a demonstration using a data set of patients called the GENIE data set, where there are over 19 cancer centers participating and over 125,000 patients with 768 indications, including over 1 million biomarkers across modalities. We're going to take that data and load it into the OMOP common data model made available via the Odyssey group. OMOP is an open source data model that includes vocabularies and a very active community. We're going to be using an open source business intelligence tooling platform called Metabase. It provides visualizations and dashboards and drill through and drill down capabilities. And then GenomOncology's Go API suite, which allows for the integration of knowledge and interpretation of variants and recommendations of clinical trials and therapies along with other knowledge. GenomOncology's knowledge base is powered by a suite of ontologies, including genes from HGNC, transcripts from the Universal Transcript Archive, diseases from Oncology and other ontologies, as well as drugs and other building blocks or concepts. We use those concepts to then create assertions. These assertions are statements of fact at the intersection of one or more concepts to then declare the eligibility of a patient for a given clinical trial, a therapy either approved by the FDA or specified as part of NCCN guidelines. We also have special statuses, prognostic rules, and diagnostic rules. It's a rules-based engine that generates recommendations that can be used for a variety of use cases. Then we also have our annotations data set, which includes open source data and then also licensed data sets as well. We release this content on a weekly basis to our clients, and that they can then pull down to their local on-premise copy and then use for a variety of our workflows. The key challenge we're facing is the amount of information around biomarkers that are required for understanding all the relevant therapies and clinical trials. As precision oncology has evolved over the years, more and more information is available, more treatments and options are available, but actually finding the right targeted option for each patient is more and more difficult. That's where GenomOncology's solutions come in. One of the key capabilities that we're going to be demonstrating in this presentation is GenomOncology's biomarker bridge. What this capability allows is for the description of variants using an HGVS superset that includes G dot, C dot, and P dot, as well as multi-omic, so not only SNVs from NGS machines, but we can also support other types of modalities from IHC and FISH. Our software is format agnostic. We can take data off of structured data files like VCFs or unstructured data files like PDFs. We support all the HGNC names and synonyms. We also support ISEN nomenclature for karyotype and cytogenetics. We have these regional concepts like exon and codon level mutations, and we support all mutation types, including missense, frame shifts, etc. And this powers our expansion capability going up and down, and that's really what the biomarker bridge describes. So in this scenario, we have our curation team is able to create new concepts in our curation tooling. For instance, they could create a rule such as EGFR exon 19 deletion. Our system knows how to parse that string and then turn that into a structured object in our database. Then when specific variants are processed by the GenomOncology platform, whether those come from a VCF file like chromosome start reft or alt, or G dots, C dots, or P dots, or maybe it's a colloquial alteration like EGFR L747del that might be copied off of a reference lab's report. All of those variants are valid in our system, and then they can be parsed and then matched to concepts like this. So this allows us to do things like curate a clinical trial where the rule to get into the trial, the eligibility criteria would be EGFR exon 19 deletions. And then the system allows for that patient to then match to that trial based on this dynamic matching capability. The system also works the other way, which will be demonstrated here, which is if you had a database of patients with all of their variants, I can go find all of the patients with EGFR exon 19 deletions by the biomarker bridge, doing that query and expanding down within variants. That is part of what powers our match API. So given a patient and their molecular biomarkers and disease type, that all gets passed into what's called our match API, and we can generate therapies and clinical trials and other recommendations that can be put onto a report. Also part of this is our disease ontology that goes up and down the schema of diseases. So using all of that information, we can then build out a precision oncology platform that supports Clinco-Genomic data. So for instance, if you had a Clinco-Genomic database, a clinical data warehouse or a data lake, and you were collecting clinical information, including disease type and age and gender and previous treatments, we can parse that information with clinical informatics. Then to take data out of a VCF file or similar file, we would use bioinformatics to parse that information and populate that in our clinical genomic database. Another option is to actually parse data out of PDFs, where we're getting just strings and doing optical character recognition and natural language processing to actually parse that information and populate our database. So given our database of both clinical and genomic information, how do we actually make use of it? Well, to do that, we need a knowledge base and an interpretation engine. That's where GenomOncology comes in. We have our curated knowledge that we've curated from a variety of sources, including the FDA, NCCN, and clinicaltrials.gov. And then we can use that information to do interpretation and reporting, decision support, monitoring and alerting, and cohort analysis. And we're really going to be talking today about cohort analysis. And GenomOncology has tools that can provide all these capabilities. GoConnect is our data integration platform that can talk HL7 and FHIR, XML, JSON. It knows how to bring in data from a variety of clinical sources and get those normalized and loaded into a clinical genomic database. We have Ignite IQ, which is our unstructured platform that can do optical character recognition, natural language processing, both rules-based and model-based, and then GoCLI, which is our command line tool that knows how to parse various genomic files and convert them to standard HGVS nomenclature. Our curation user interface is available to be installed as well, so you can curate your own rules. We have clients that are curating what are called private protocols behind the firewall at their institution to add to the knowledge that's publicly available on clinicaltrials.gov. Our knowledge suite is available using an API. So we have a REST-based API, and what I'm going to be demonstrating today is a SQL-based API. Our pathology workbench is our oldest product. It's been around for almost 9 years now, and that helps pathology labs take data off of a sequencer, validate the quality and the variants, interpret the variants, and interpret the whole case to then generate a custom white label report with their logo and colors and really their demonstrated interpretation. We have a molecular tumor board, which supports academic medical centers and reference labs that are working on hard cases to present the information, the genomic information, in context of a case, to then have a meaningful discussion and then make recommendations. Precision decision allows for treating oncologists to look at a patient in the context of their disease and find relevant trials and therapies, but it also allows for the alerting of new rules or new therapies or trials that have become available for their patients, and then also to help with clinical trial feasibility analysis and clinical trial enrollment and recruitment. And then Genome Analytics, which is our big data platform that has visualization and dashboarding capabilities. And this is all stored within the GenomOncology data architecture. But wouldn't it be cool if our clients could actually bring their own database, right? Not have to load things into GenomOncology, still take advantage of that capability of our knowledge suite, our API suite, but then also use whatever analytics tools that they have. So whether it's Tableau or Power BI or some of the other tools that are available. So to do that, what we really want to be able to do is unlock the Clinco-Genomic data stores that our clients have, allow them to leverage their BI tools that they already have licenses for, but then use GenomOncology as a knowledge layer that powers that full connection between BI and their actual database. So for this demonstration, I've brought down the common data model from the Odyssey project and Athena, brought down their vocabularies and data structures and loaded those into a Postgres data store. I then brought down the GENIE data, right, the actual clinical markers for the 19,000 patients and their biomarkers. And then GenomOncology, an instance of our knowledge base, and also loaded into Postgres. And then basically unlocked the ability to query the clinical and biomarker information using the GenomOncology SQL API. This will allow for interpretation of both the variants and then applying those to at a case level to generate recommendations for therapies in this demonstration. And all that's going to be viewable using Metabase, which is an open source BI tool. So OMOP, for those of you that aren't familiar, is a common data model that supports federated query across institutions. There's thousands of institutions, I believe, that are using this data model and then able to share with each other. And it basically provides database tables and schemas for and it does a really great job at clinical data, standardizing all the information to standard vocabularies, and then they build tools on top of that to allow querying, shared querying across patient records. There's a tool called Athena for navigating their vocabularies, the concepts. I downloaded some of the models, specifically Oncology, because that's how the GENIE data set is currently coded. So they're using Oncology for indicating disease type. So I brought down Oncology for this demonstration. And then I mapped the GENIE data to OMOP, using the data set that came from the Synapse website. I was able to map that into OMOP, and these are this is an example of a specific case that was mapped in, and what fields that I used to map them. And then for loading the GENIE biomarkers, right? So GENIE provides over 1.4 million biomarkers that include SNVs, CNVs, and fusions. However, OMOP, the common data model, currently lacks genomic support. There is a working group that's working through that. They meet every week or every other week. They have two approaches that are under consideration. This approach is different than those, and I'm going to walk you through how I accomplished this. So the way that I made this work with GenomOncology's capabilities and the OMOP data model is you just need to make a simple table, right? You can name it however you want. And then you can store the markers in the format that you have them, right? So if you've got biomarkers off of a VCF file, you would just store them in chromosome start ref alt. If you have them from HGVS format, that's even better because they're already kind of normalized. Or if you just have them from say a Foundation report or a Tempest report, you can just copy in the gene name and the amino acid change or mutation type. And then the foreign key to the specimen table, using the sample identifier to tie everything together, and then any relevant information you have for the biomarker, including something like VAF. And VAF is actually calculable given the GENIE data that's provided. So I went ahead and loaded in the GENIE biomarkers using some basic minimal transformation. SNV mutations were calculated using chromosome start ref and alt. They do provide some HGVS. But for this demonstration, I'm ignoring the provided one to take advantage of GenomOncology's annotations, calculated the VAF, and then parsed the CNA matrix file. If you have any trouble with doing this parsing, please let me know. My email will be at the end of the presentation. And then calculated fusions, and then annotated them using GenomOncology's Annotate SQL API, which I'll talk about in a moment. So annotate is one of the functions that are available from the SQL API. And basically it takes the marker, whatever format you have it in, whether it's chromosome start ref and alt, or if you have a HGVS, it can then take that information and then basically parse it and convert it to proper HGVS with the right transcripts. And we can support multiple transcripts, and we can support both GRCH37 and 38. And then we can bring in also a variety of different IDs and scores from different annotation sets, and these are just some examples. Then we can also support the expansion capability of the biomarker bridge. So for instance, we can go up the chain saying, for a specific variant, which from the earlier example, EGFR L747del, we can use expand up to find out that it is an EGFR exon 19 deletion, an EGFR mutation, and an EGFR deletion. So all three of those are valid alteration concepts that can be extrapolated from that specific concept. We can also do expanding down. It means we can go find all of the EGFR exon 19 deletions that are in the GENIE data set. And these are the first 4 records that I did that show up when you do that query. And then there's the match capability as well. So once again, you can select data calling our match function, part of the SQL API. This is built into the Postgres database, but it's just basically SQL. So we could port it to other databases as well, and then also work with you to integrate with a data lake as well. And in this case, we're bringing out various drug matches with just a select number of the fields for demonstration purposes. And so using that API with annotate, the expansion capabilities of the biomarker bridge, and match, I put together a simple demo using Metabase. Metabase is a great open source tool, lots of database connectors that you can see over here, including Postgres and some of the different cloud providers. Lots of different database connectors, lots of different widget types, and basically use the tool to then build your visualizations and then tie them together into a dashboard. And those dashboards allow for drill down, which is narrowing down the values, and then drill through, which is going from one screen to the other. It also has type ahead capabilities, and you can also embed these widgets into your applications with a license. So now I'm going to demonstrate how this works. So I have Metabase running locally. The first one I want to show is the OMOP vocabularies. So I loaded in pretty much all of OMOP, and you can see here the different vocabularies. And so then these visualizations or pie charts. Over here is a table view of it. I also made it so that when you click through, you can go to the Athena website. So let's go ahead and find all of the Oncology records. And you can see here, these are all the values in Oncology. And so if I were to click on one of these, it would actually open up the Athena website, and you could see where it fits in the vocabulary. I'm going to go back to look at the patients within the GENIE dataset, and you can see the breakdown of disease types and gender, race, ethnicity, and then the top biomarkers and top mutation types. What I'm going to do now is actually show how the GenomOncology platform applies here. So if I type in non-small cell lung carcinoma, this is a type of disease, and then do a filter, notice that the diseases that come back are not just non-small cell lung carcinoma. That's because it's actually running through our disease ontology to bring back all of the patients that have a subtype of non-small cell lung carcinoma. In this case, lung adenocarcinoma is the most populous version, but you can see there's other disease types as well. And then over here you can see the different patient records from GENIE with their GENIE ID and code and other values. If you were to click on each of these items, you can actually then do what's called drill down. So I'm drilling down into this group based on the items that I'm clicking. And then from there, I can also look at the different care sites as well. So I could click on this and just see the patients for Dana-Farber that are female and then Black or African American. So I can clear these, and then those are values that I'm filtering on as basically a hard filter on the string names. Non-small cell lung carcinoma is taking advantage of the disease ontology, but then the biomarker bridge can be demonstrated by, once again, using the EGFR exon 19 deletion concept and filtering. So notice here that we've got, EGFR is the top mutation type, and we have different, mutation types below that. if I were to actually click through this one, you can see here that this patient has an EGFR deletion in that region of exon 19. And so you can see that patient's got 14 mutations, and I'm bringing back all of their alterations on this other dashboard called GENIE Biomarkers. So that was an example of a drill through where I clicked from one dashboard into the other. I can also click on the way I've set up this dashboard is I can click on the patient's name, and that brings up another dashboard called Go Therapies. And this is actually running our match algorithm. So the match algorithm is finding the patient, getting their disease type, getting their 14 biomarkers, and then calling our match algorithm to return back all of the potential therapies that can be considered. Now, this use case doesn't demonstrate match to its fullest capability. There's additional logic that would be on top of this to kind of normalize and sort the information that can then be best presented in our pathology workbench tool or other solutions like Precision Decision. So that's the demonstration. Some of the key takeaways are you can use your existing data architecture, whether you have a data lake or a data warehouse, use your existing business intelligence tooling, whether you're using Looker, Metabase, or Tableau, or Power BI. There's reduced effort for loading the markers, right? So one of the key things is that our clients are challenged with are normalizing variance, right? They're getting variance from a variety of sources through PDFs, XMLs, JSONs. Our software basically takes away that work where you're just loading the biomarkers in as you have them, and then we're able to normalize them in place. So you can keep that original version of it, but then also have the proper HGVS and other annotations. It's ontology aware, so we understand the biomarker bridge, the disease ontology, and we can use those for querying directly in SQL. And we find that data scientists like working with SQL when they're building out their dashboards and other analytics. And then the annotations that we provide are updated on a quarterly basis. And then we have a comprehensive knowledge base that is updated on a weekly basis, including clinical trials from clinicaltrials.gov. And SQL, it's high performance and it allows data scientists to work in a language that they're comfortable with.